This is Business Calculus, section 4.3, which is all about taking derivatives of exponential functions. When you're taking the derivative of an exponential functions, you are going to have base e's, but you are also going to have every other base in the free world. Right now, we're just going to focus on our e to the x's, or our e to some power. Just kind of a little refresher for us. When you're looking at exponentials, we can follow all of those exponential rules that we learned in algebra. For instance, if you have exponentials that have the same base, if you are multiplying them together, you can join them together with addition. So you're adding those exponents. When you're dividing, you're actually subtracting those powers. Make sure that the one that was on the bottom has that negative exponent. We also have some simplification properties. If you're taking the natural log of e to the x power, that natural log is actually log base e. It's going to cancel out this exponential base of e, which is going to leave us with that power. And likewise, that property goes the other direction. If you've got an exponential with a power that's a natural log, that e and that natural log are going to cancel each other out, and you're going to get that x. So all of these properties we're going to be able to use when we are taking the derivative of exponential functions. What makes it an exponential function is that your base is a number and your power is a variable. And like I said, at first here we're going to talk about our favorite exponential function, which is e, the natural number. When we take the derivative of e, we're going to rewrite that exponential as is. We're not going to do anything but rewrite it. Then we're going to multiply by the derivative of the exponent. Okay, so that's going to be the fun part. Rewrite the exponential as is, then multiply by the derivative of the exponent. So let's see what that's going to look like in a few of these nice, pretty little examples. Let's move that to the middle there. All right, so look at my exponential. It has a 3x minus 3 power. So when I go to take the derivative, and I always want to put that hash mark there so people know what I've done, when you have the exponential to take the derivative, you rewrite the exponential as is, don't change a thing, and then you're going to multiply by the derivative of its power. Well, the derivative of 3x minus 3 is just 3. Now, we don't have to fight the urge to multiply those together as much as we will when we have other exponents, or other bases rather. But when you're looking at your exponential, this 3 and this e, you can't multiply those together because remember your order of operations, you have to do powers first. So we would have to be able to simplify this first, and then we could multiply it by the 3. Well, because we have a variable still in the power, we're not going to be able to simplify that. So fight the urge to multiply bases through. All right, so number 2, we've got an exciting exponent. We've got 6x minus 1/2 x to the 6th power. So when we go to take that derivative, we're going to start off exactly the same way every single time. We are going to rewrite that exponential as is, don't change a thing, and then you're going to multiply it by the derivative of its power. Because I have more than one term now that I'm taking the derivative, okay, I had 3x minus 3, but the derivative of that was just 3, so I didn't need those extra parentheses. Here, my derivative of 6x is going to be 6 minus, bring that 6 down times the 1/2, so that gives me 3x to the 5th power. So here I do need those parentheses because I have 2 terms in my powers derivative. Okay, in order to write this as our final answer, there's not much we can do to simplify that. You can rewrite it with that derivative in front, but we could have easily have left it just as it was right up here. Okay, so there's my final answer. Rewrite the exponential as is, multiply by the derivative of its exponent. Well, now that we know how to take the derivative of exponential with the base e, we're just going to kind of practice that with everything else we've learned to derivatize. Okay, so y here, I've got a natural log of x here. I've got everything going on at the same time. But notice it's an exponential, so rewrite that exponential. And then you're going to multiply it by the derivative of its exponent. Well, the derivative of 1 is 0. The derivative of negative natural log of x. Remember, we just learned how to take the derivative of logarithms in section 4.2. So with that, you rewrite the coefficient as is. Then remember, you take 1 over what you're taking the log of times the derivative of what you're taking the log of. The derivative of x is 1. So we get a pretty little guy. We've got negative 1 times 1 over x times 1, so that's just negative 1 over x. And then times e to the 1 minus natural log of x. Now if you want to, you can put that e on top. That negative is understood to be a negative 1 in front of there. Just a little bit of math shorthand. And that's perfectly fine to leave your answer. You could have left it like you had it right up here as well. Okay. All right, so number 4, we have f of x equals the natural log of e to the 3x minus 8. Okay, so we've got ourselves a logarithm. When you take the derivative of a logarithm, you take 1 over what you're taking the log of. And then you're going to multiply it by the derivative of what you were taking the log of. So the derivative of e to the 3x, that's going to be e to the 3x times the derivative of the power, which is 3, minus the derivative of 8, which is 0. And I can write these one on top of the other. It makes it look a little bit more simplified. Oops, don't know where that 3 came from, sorry. E to the 3x minus 8. And remember that minus 8 is not a power, okay? He's in the denominator as a term just like e to the 3x's, okay? Let's bump up the excitement just a little bit more. Oh, look at that. Number 5, we have a chain rule. So we actually have 2e to the 3x plus x all to the 1/2 power. Remember how we handled chain rules? You do the derivative of the outside, so do that power rule. Bring that 1/2 down. Don't change anything on the inside. Subtract 1 from its exponent, so that's negative 1/2. Times, now we get to do the derivative of the inside. So the derivative of 2e to the 3x, rewrite your exponential, 2e to the 3x times the derivative of the exponent, which is 3, plus the derivative of x, which is 1. Now, when I took the derivative of the inside, what I had was 2 terms worth, so please make sure you put those parentheses around there. You're multiplying that whole 1/2 times 2x e to the 3x plus x times, or to the negative 1/2 power. You're multiplying that whole thing by what we just took the derivative of. All right, so it looks like this guy with the negative 1/2 power, he's going to go down in the bottom. Since it is a 1/2 power, I'm going to change it back into a radical. You don't have to. And then I have that 1/2, so I really have 2 on the bottom. Now, inside where I took the derivative of what was inside in that chain rule, that 2e to the 3x times 3, I can multiply that 2 and that 3 together. I couldn't multiply anything through with that e though. So this is as nice as this is going to get. But it's right, and being right makes it look a little better. Don't forget, all of that is under that radical. All right, so now that I'm working on number 6 here, let's move that over. We have a quotient rule. So you have to follow the quotient rule. Gosh, that just seems to make sense. So we're going to take the derivative of the top. Well, the derivative of 15 is 0 times the bottom as is, minus the derivative of the bottom. Well, the derivative of 2 is 0. The derivative of e to the x is e to the x, times the derivative of x, which is just 1, times the top as is, all over the bottom squared. We just need to simplify that a little bit. 0 times anything is 0. I have negative e to the x times 1 times 15, so I have negative 15 e to the x. And then all of that is over the bottom squared, which you do not have to FOIL out. So even though that was a quotient rule, it turned out to be not too bad. Okay, let's see if we can do a product rule. When you're looking at this, you have 10 times x squared times e to the x. You want to split those variables apart, so I'm going to put that multiplication right there because I'm going to take 10x squared as that first guy, what we call f. I'm going to let e to the x be g. Okay, so remember our formula for the product rule, the derivative of f times g as is plus the derivative of g times f as is. Make sure you're telling people, hey, this is the derivative. So the derivative of 10x squared is 20x times e to the x as is plus the derivative of e to the x. What's kind of funny about that is the derivative of e to the x is e to the x. So it kind of looks like we forgot to take the derivative, but we didn't. He just happens to be his own derivative. And if you think about it, that's kind of neat. E to the x. So that would be as far as we can go. So don't forget, you still have product rules and quotient rules and chain rules along with our exponentials. Now number 8 looks like it's going to be one of those problems that isn't much fun. It looks like a quotient, so it looks like we'd have to do the quotient rule. But look, we have the same base on the bottom as we do on the top. So remember in our slide number 1 where we were talking about right here, base on top, same as the base on the bottom. We're dividing, so we can just subtract those exponents. So let's do that. We're just simplifying. We have not taken a derivative, so notice there's no prime here. So if I take this and I subtract their exponents, it's going to be 2 plus x minus 2 minus a negative x, so that's a plus x. So if I simplify that, that's just going to be e to the 2x. So that nasty problem we started with is just e to the 2x. So now when I go to take the derivative, and note you know I'm taking the derivative because I have that little prime there, e to the 2x, you rewrite your exponential and then multiply by the derivative of that power. So my answer turns out to be a nice pretty little 2e to the 2x. Final answer, fabulous. All right, so now, when we go to take the derivative of an exponential whose base is not e, it's very close to being the same thing. In fact, if you look at it, this is exactly the same thing we did with e to the x. You rewrite the exponential as is, and then you multiply by the derivative of the exponent. There's just one small change, and that's this little beauty right here. So that natural log of b. So whatever your base is, you're going to have to start off with the natural log of that base times the exponential as is times the derivative of that exponent. So let's look at a couple of these examples just to see how good or bad it's going to get. All right, we're going to start off with a nice pretty easy one. We've got g of x is equal to 4 to the x power. So when I take the derivative, I start off with the natural log of the base that I do have. So the natural log of 4. Now I'm going to write it like the natural log of 4, but please understand there are parentheses around the 4, so nobody can get inside with the 4 ever. Then I multiply by my exponential as is times the derivative of that exponent, which is 1. So the best I can do with this, if I don't want to write parentheses out, is put the 4 to the x in front of the natural log. If I don't, then I will have to make sure that I put those parentheses around it. Okay. Now when I look at number 12, once again, that kind of looks like that's going to be a quotient rule. But remember the property we used when we had e to the whatever power divided by e to the whatever power? We're going to use that same concept. If your bases are the same, then you can subtract those exponents. But if your powers are the same, you can simplify that way too. Because they both have an x for their power, I can rewrite it using parentheses because we know that property from Algebra 2. It's exactly the same concept. But now that I have my parentheses around the 8 halves, I can simplify that 8/2, which is 4. So really, 8 to the x power divided by 2 to the x power is 4 to the x power. And this is much easier to take the derivative of. Heck, we just did it. If I don't simplify it, then I will absolutely have to do the quotient rule. So once again, and try not to do what I just did in this problem. Okay, look at what I did. I got a little sloppy. My x got a little big. Make sure that anybody that looks at your problem can tell that x is small and high. It is an exponent. So watch yourself if you're writing like me. Watch it. Be careful. All right, let's do a couple more examples because this isn't so bad. All right, number 13 here. I've got those nice pretty parentheses around there because now that my base is an e, it kind of makes it a little bit more difficult to figure out what the exponential is. So they'll put parentheses around it usually. And you got yourself a product, so you have yourself a product rule. All right, so it's x squared times my 0.2 to the x power. I'm going to take the derivative of x squared, which is 2x, times my exponential as is. I'm going to keep with those parentheses. I kind of like them. Times the derivative of my exponential, which is, you rewrite it, and then multiply by the derivative of your power. Back it up. Remember, this base is not e, so we start off with the natural log of the base we do have. Then times the exponential as is, times the derivative of the exponent, which is 1, times the first guy as is. Now when I look at that, boy, I'm going to put those parentheses around that natural log of the 0.2 there so that I remember that it's natural log of 0.2. Nobody else gets to go in there. That 0.2 is going to stay all alone inside that natural log. Then I've got my 0.2x times 1 times x squared. There's a lot of points in there for multiplication and decimals. It gets kind of crazy. So let's rewrite it so it looks a little bit better. I kind of like this 2x, and I like the parentheses with the 0.2 to the x power. Then these guys, I'm going to bring this all out in front. So I'm going to have my x squared times 0.2 to the x power times my natural log of 0.2. That way I don't need quite as many of those little decimals or little points that we're using for our multiplication, those dots. It just makes it a little bit easier for us to read it. That is the entire answer. Okay. All right, so let's look at example 14 here. Woo, 13 got a little big. We just have a plain ordinary exponential here. So this one's actually easier than number 13. Okay, the base is not e, so start off with the natural log of the base you do have. Go ahead and put that in parentheses because nobody's getting inside there with that 2. Times the exponential as is, and then times the derivative of your exponent. The derivative of 9 minus x is just negative 1. Okay, I would for sure put that negative 1 in front, and then times my 2 to the 9 minus x power, natural log of 2. Okay, now something I want you to be aware of. Your negative 1, I can rewrite this because negative 1 times 2 to the 9 minus x power is actually this guy right here. But I don't want you to think that we actually multiplied the negative 1 and the 2 together because we did not. But remember, 1 and negative 1 are a little bit different. I can write negative 1 times x, or I can write negative x, and people understand that it's the same thing. What I want you to be aware of is if you had this, say we had 3 times 4 to the x power, it is not and never will be 12 to the x power. If you have 3 times 4 to the x power, it's going to stay 3 times 4 to the x power, because we have to do exponents before we do multiplication. So just be very, very careful. All right, so let's do just a couple more. When I look at this guy, it's actually y equals 4 to the x to the 1/2 power. Holy cow, an exponent with an exponent. That is crazy good. So we're just going to focus. So I'm going to take my derivative. My exponential has a base of 4, so I'm starting it off with the natural log of 4 times my exponential as is. Then I'm going to multiply by the derivative of the exponent. My exponent is x to the 1/2 power, so that would be 1/2 x to the negative 1/2 power. Okay, and then let's see if we can make that look just ever so slightly better. Not a lot we will be able to do. We have our 4x to the 1/2 power, which I'm going to change back to a square root because that x to the 1/2 power, I'm having enough trouble keeping my power where it is, let alone it having a power. Times my natural log of 4, and then that 1/2, that 2 is going to be on the bottom. That x to the negative 1/2 is also going to be on the bottom. Now remember, this 4 and this 2 you cannot simplify because that 4 has an exponent that you have to take care of before you do any kind of division, etc. Okay? So let's look at our last example here. We've got a mix of some natural logs and some exponentials. We've got a little bit of everything. But note, we've seen product rules, quotient rules, chain rules, power rules, logarithms, exponentials. We've got it all now. So when I take the derivative of 2 natural log of x, that's going to be 2 times 1 over what you're taking the log of times the derivative of what you're taking the log of. So that's this term right here, plus, let me change colors here, and then the derivative of our exponential there, natural log of the base we do have, times our exponential as is, don't change a thing, times the derivative of that exponential, which would be just 2. Okay, and then if I want to rewrite that, try to make it look a little better. 2 times 1 times 1, that's going to be 2 over x, plus, I'm going to pull that 2 in front, and then I'm going to put my parentheses so everybody knows that's the only thing I'm taking the natural log of, and then write my exponential behind. There's a lot of different ways you can write it. Just make sure that you put your parentheses up so people don't think you mean something other than what you do mean. All right, so that was our finding the derivative of exponents with bases of e or bases of everything else. I'll see you back in class. Bye.